Let's talk about this problem from IOQM 2022. We will learn a lot using this problem, so you can grab a pen and paper and work with me on this. So what are we going to learn? First of all, we will talk about casework. Secondly, we will use the star and bar method. And finally, we will do a little bit of number theoretic trick which categorizes numbers. So let's do all of these together, and we will learn all of these using this problem number 24 from IOQM 2022. So here is the statement of the problem. The statement says that there are 52 balls and 4 distinguishable boxes. So there are 4 distinct boxes like this. I'm drawing in different colors, and 52 balls which are identical. The balls are identical, and we want to distribute these 52 balls in these 4 boxes, and the question is how many ways we can do that. But there are some additional conditions. So the first condition is no box is empty. So to satisfy that condition, what I'll do is I'll just put one ball in each of these boxes. That we can do, just remove these 4 balls and put them one in each box. So now no box is empty. We will start the distribution process after doing this. So now we have 48 balls left. 48 balls left. So basically these 4 boxes should now add up to 48. The number of balls in these 4 boxes should add up to 48 because I've just put one ball in each box, right? The second condition is that the difference of the number of balls of any two boxes, so if you just take the difference of the number of balls in red and yellow box, the difference is not a multiple of 6. A multiple of 6 is not a multiple of 6. Okay, let's see how we can use that. So here I will talk about something called the categorizing of numbers. So if you take the number 6, if you divide any number by 6, the possible remainders are 0, 1, 2, 3, 4, 5, right? If you divide any number by 6, these are the possible remainders: 0, 1, 2, 3, 4, 5. Now listen to this very carefully. If the difference of two numbers is divisible by 6, then the numbers themselves would produce same remainder when divided by 6. The numbers might be different, but they produce same remainder when divided by 6. If you think about it, this is very simple. Suppose this number is 6k1 plus r1 and this number is 6k2 plus r2. Now if you take their difference, what you get is 6k1 minus k2 plus r1 minus r2. So if this quantity has to be a multiple of 6, this little portion r1 minus r2 must be 0, right? So this is a very important step of this problem. Make sure you understand this absolutely clearly. If the difference of two numbers is divisible by 6, then their remainders must be same. The remainders that they produce when divided by 6 must be same. Okay, so now let's get back to this problem. I will just draw this equation one more time. I'll just draw this one, copy this, and just draw it here. So let's see what is the remainder produced by the red one. So it's 6 times some r1, 6 times some k1 plus r1. Whatever the number of balls in this red box is, I can write that as 6 times some quotient plus r1. Any number can be written like that. This one can be written as 6 times k2 plus r2. This one can be written as 6 times k3 plus r3. And this one can be written as 6 times k4 plus r4. If you give me any number, let's say 50, I can write it as a multiple of 6 plus some remainder. So this is 6 times 8 plus 2. This is the quotient. This is the remainder. So I can do that for any number. So I can definitely do that for number of balls in each of these boxes. Now this will be helpful because now I can demand that these remainders are all different. Let me write that. We want the remainders to be different. Why? Because if all the remainders are different, then the difference of any two of them will not be divisible by 6. That's what the problem says. You don't want the difference of any two of them to be divisible by 6. So the way we enforce it is by making sure that the remainders are all different. Okay, so now we have set this up. Let's write it down. 6 times k1 plus k2 plus k3 plus k4 plus r1 plus r2 plus r3 plus r4 equals 48. Right? So this sum is equal to 48. So r1 plus r2 plus r3 plus r4, the sum of the remainders is 48 minus 6 times k1 plus k2 plus k3 plus k4. Now here comes a very crucial step. Notice that the right hand side is a multiple of 6. The right hand side is a multiple of 6. So it's 6 times some number. Which means the left hand side is also a multiple of 6. A multiple of 6. It's not only a multiple of 6, we also know that it is less than 48. It's 48 or less. Why? Because this is right hand side is 48 minus something. So the left hand side is also 48 minus something, which means it's 48 or less. In fact, we can say more about the left hand side. What are the possible remainders? The possible remainders are 0, 1, 2, 3, 4, 5, right? If you divide any number by 6, the possible remainders are these 6 numbers. So the smallest, remember all of them needs to be distinct. So the smallest that you can go, smallest value possible, you pick 4 numbers from this list, add them up, the smallest number that is possible is 0 plus 1 plus 2 plus 3, which is 6. And the largest value that is possible by adding 4 numbers from this list, I'll just take the 4 largest numbers, 2 plus 3 plus 4 plus 5, which is 14. So the sum of R1 plus R2 plus R3 plus R4 ranges between 6 and 14, right? But we also want them to be the multiple of 6. So there are exactly 2 possibilities for the sum of R1 plus R2 plus R3 plus R4. And these are, and here starts the casework. Case 1, R1 plus R2 plus R3 plus R4 is equal to 6. And case 2, R1 plus R2 plus R3 plus R4 is equals to 12. Now you can take a pause and sort of reflect on how beautiful this is, this analysis is. We figured out that this sum has to be a multiple of 6 and must be 48 or less. And then we found out how large, small can it get and how large can it get. And then from this range, we just chose the 2 multiples of 6. So that's great. So now in case 1, you can sort of check this by observation that the only possibilities of these 4 numbers are 0, 1, 2, 3. And in case 2, the only possibilities of these 4 numbers, there are 2 possibilities actually. One of them is 0, 3, 4, 5. That adds up to 12. Or it's 1, 2, 4, 5. So it's like a little bit of calculation or observation that you will be using. So these are the only 3 cases which we will be interested in. The only 3 cases. So this is case 2A and this is case 2B. Okay, we are almost there. We are almost there, very close to the solution. So if let's write bring this back in the picture. So I'll copy this, go to a new page. So if this is 6, then we have 6 times K1 plus K2 plus K3 plus K4 equals to 48 minus 6, which is 42, or K1 plus K2 plus K3 plus K4 is equal to 42 by 6, which is 7. So we want the number of non-negative integer solutions to this equation. What equation? Well, K1 plus K2 plus K3 plus K4 equal to 7. Now this is where I'll be using the stars and bars method. the stars and bars method. So it says that the number of non-negative integer solutions of this equation is equal to, and this is a standard formula in combinatorics. If you want to learn more about it, you can refer to the video in the link in the video link in the description. This is 7 plus 3 choose 3. So each of these plus signs is a bar. So you have 3 bars and 7 stars. So the formula is number of bars plus number of stars choose the number of stars or number of bars, doesn't matter, same thing. So this is 10 factorial by 3 factorial times 7 factorial. So we can quickly calculate this. This is 7 factorial times 8 times 9 times 10. And this is 7 factorial times 3 times 2 times 1. So you have this as 3, this is 4. So total is 120. So there are 120 solutions for this. And we know that R1 plus R2 plus R3 plus R4 is 6, means there are the values that we can use is 0, 1, 2, 3, only these 4 values. So there are 4 factorial ways of arranging these 4 numbers as R1, R2, R3 and R4. So 4 factorial ways means 24 ways. So 24, and we found K1, K2, K3, K4 can be distributed in 120 ways. So we have case 1, the number of possibilities is 120 times 24, which is 120 times 24 is 2880. That's case 1. Exactly in the same way, you can do the case 2A and case 2B, all the 3 cases. So case 2A, I'll do it rapidly. Case 2A, this R1 plus R2 plus R3 plus R4 is 12. Then K1 plus K2 plus K3 plus K4, K1 plus K2 plus K3 plus K4, this one will be 6 instead of 7. Because instead of 48 minus 6, you will have 48 minus 12, and then you can divide by 6 to get the answer. So this is, and the number of solutions for this is 9 choose 3 by stars and bars method. We have 6 stars and 3 bars. So this comes out to be 9 factorial by 3 factorial times 7 factorial, 6 factorial, which is 6 factorial times 7 times 8 times 9, and 6 factorial times 3 times 2 times 1, so 3, 4, so that's total 84. So for case 2A, we have 84 times 24. Of course, the remainders can be redistributed in 4 factorial ways. So we have 84 times 24. Let's see. 12 times 7 is 84. So 84 times 24 times 2 plus 2880. So case 2b is also the same thing. So we have, this is 2016 and this is also 2016. So total we have 6912 cases. So the final answer is actually the sum of these two portions, because they wanted it in integer values. So 69 plus 12, that's 81. So this part is not that important. What's important is that there are 6912 cases in total. That many number of ways to distribute these balls into these boxes. So quite a nice problem, involves different concepts. Casework, we did a lot of that. We did the stars and bars method, and we also categorized numbers and analyzed their different forms in terms of 6. Okay, so I think you should be able to do problems like this now. If you have more questions regarding this problem or any other problem, let us know in the comment section. Thank you for watching this video. I'll see you in the next one.